grateful to be able to present this work on behalf of me and my team here at Georgia Tech, here in the Lunar Lab. Our work is called MI-HGNN, Morphology-Informed Heterogeneous Graphical Network for Legged Robot Context Perception. So the motivation for this work, we're working with legged robots, which are significantly capable to traverse these complex and unstructured environments. The problem we're tackling is contact perception, knowing the forces at your feet, or maybe knowing if your foot is in contact with the ground or not. This can be really useful for a variety of scenarios, but primarily for potentially maintaining balance or responding to disturbances when you're potentially moving really fast or navigating in these difficult terrains. So previous methods for doing this, you could just slap a built-in sensor on the bottom of the foot, like this one right here, and just measure the forces. But unfortunately, these are often quite noisy and break quite easily. So you could do instead some model-based estimation, use the dynamics model of the robot to try to estimate it, but these can be sensitive to sensor noises or unmodeled dynamics. Another option is to use learning-based methods to try to overcome these sort of unmodeled things, try to just learn them directly from data. But we all know here, we're at ICRA, we do not have the data necessary to train something on the level of ChatGPT. So we in this work are inspired by geometric deep learning. Take some sort of model-based information that we know about the world and constrain our learning method so that we don't need as much data. So we propose MI-HGNN, Morphology-Informed Heterogeneous Graphical Network, and we constrain our learning problem with the robot morphology or the robot structure, as you can see on the right, kind of taking the structure and creating the graph. And we find empirically that this leads to tons of really cool results that we wouldn't necessarily have expected, including performance, generalization capability, model efficiency, and sample efficiency. So how does it work? Well, we take our robot agent, we extract the kinematic structure, and then we create a heterogeneous graph with 3 different node types. And if you'll notice, each of the nodes corresponds to a local joint in the kinematic structure. Then, after we have this heterogeneous graph, we take our proprioceptive sensor information, like our IMU data or our joint encoder information, and embed them into the corresponding nodes in the graph with heterogeneous encoders. After we do that, we do some sort of multimodal sensor fusion by doing learned message passing. So you have our individual blue node here, and it's going to fuse its information with its neighboring yellow nodes through message passing, which is learned. And these learned weight matrices are aware of the node types that it is operating on in the graph. Finally, after we've done all that, it's pretty easy to slap a decoder on the end and extract the contact information we want, whether it be forces or whether it be the contact state. We train our methods using supervised learning, so nothing surprising there, but there are kind of 3 notable aspects that make our model work. First is its heterogeneity. The embeddings on the front, the heterogeneous encoders, and the message passing are both aware of the heterogeneous nature of the current node types and allows it to do this kind of multimodal sensor fusion. Second is the data correlation. As the graph is constructed from the morphological symmetry of the robot, it can use this information as a prior and exploit it during learning. And finally, symmetry. It turns out if your robot's morphologically identical across different limbs, this correlates to graph symmetry, as shown in the graph on the right, which then becomes shared weights. These shared weights mean you can train a model, that much faster, and it's a lot more generalizable. So to prove it works, we've evaluated on multiple experiments, but this is a classification experiment on a real-world mini cheetah robot. It has various gaits and different terrains, and our test sequence includes 5 different unseen terrains to evaluate its generalizability. We compare against 3 different baselines, 2 being similar geometric deep learning methods, just like ours, the ICRA and CNN in that kind of light purplish color. And the bottom is CNN, a pure learning-based method, and ours is orange. And as you can see on the very right, our state accuracy is at 87.7%, beating the second best by a whopping 11.3%. In terms of model efficiency, we're actually able to do this with just 1/4 of the parameters of the ICRA and 1/7 of the parameters of the CNN, which we attribute to, again, those shared weight matrices. In terms of sample efficiency, we still get this very high performance, even with 10% of the training data. And let's say, you deleted all your data somehow, you're only left with 2.5%. Well, guess what? We still match the performance of the other 3 baselines, even with that few samples. Finally, we did an ablation study, but in terms of time, just to summarize this, if you use our smallest model right there I circled, we can actually still beat the second best model by 8.4% and use 1 in 1/500th approximately of the parameters. So 75,000 parameters to 5 million parameters, and we're still beating it. In terms of time, I'm just going to conclude really quick. Our model is the MI-HGNN, and although we only applied it to legged robots here, it can be applied to other robot structure and other data sets with their open source repository. So we invite you to see how morphological symmetry can improve your robot. Thank you.